Okay. Hi, everybody. So it was gently pointed out to me after yesterday's session that I didn't start by introducing myself. My name is Kelly Street. I'm a professor in biostatistics. I just joined last August, so I've been here a year now. I'll be teaching public health, PM 566, Intro to Health Data Science this fall. And yeah, I'm really excited to be talking about R. And thankfully today, I'm going to try to keep things to a little bit lower, like slower pace. We had to get through a lot yesterday. It was very frantic. And a lot of that is because, as I said at the beginning, I think too many people start on fairly advanced topics when teaching R. A lot of people jump right into data frames and how to manipulate fairly sophisticated data objects. And that's not really where you should start when you're learning a new language. You should start, at least in my opinion, you should start with the basics. And so I had to sort of introduce those basics before getting to the point where past iterations of this bootcamp have started. Anyway, today should be a little bit more chill. I'm gonna just sort of revisit some of the things that I had to go over very quickly at the end of yesterday so that we can be hopefully all on the same page. I know that some people missed yesterday's session and so might have watched videos from previous years, which wouldn't have covered indexing and wouldn't have covered vectors and sort of basic objects. But just to hit some of the highlights, if you want to install a package from CRAN, you can use this install.packages and then the name of the package. You can do that a lot, super helpful. Every time you update your R version, which you should do pretty regularly, a new version of R comes out every 6 months. Whenever you do that, you're gonna have to reinstall all the packages that you use. And then once you've installed a package, you can load it into your current session with this library function. And functions are a very basic unit of code, right? Functions are how you do something. And so most of them are verbs. I don't really like this library. There's actually an alternate one called require that does exactly the same thing as library, but for reasons, historical in nature, everybody uses library. If you want to find, if you have questions about how to use a particular function, you can find the help documentation by typing question mark and then the name of that function, and that'll pull up this help documentation. I'm going to minimize this because it's really annoying. And then subsetting, we talked about a little bit, but just to recall, if you've got a one-dimensional object like this, so X is a vector of the numbers 1 to 10, you can subset that with square brackets. And there are a lot of different ways you can subset, right? You can pull out specific elements. So if I pull out the third element, it gives me that. You can pull out ranges. I can pull out the third through the ninth element. And you can also pull out based on a vector of trues and falses. So if I say X greater than 5, it'll give me those values which are greater than 5. If you have a two-dimensional object, so now I'm going to make Y matrix. This Y is now a matrix. You can see across the top and bottom, they even sort of give you some clues about how you would subset this matrix. This is now a two-dimensional object. So when you subset it or index it, you need to use that comma to separate the rows that you want from the columns that you want. And you can get as fancy as you want with this, right? If you want one particular element, I could pull out, y22 should give me that 7, right? And it does. But just like before, you can subset with trues and falses. You can subset with ranges. There's lots of different things you can do here. So this is a very powerful tool. We're going to see in a minute why I'm getting back to this. But today we are going to work with an actual data set. And so that's why I showed how to install and load the ggplot2. Oh, I misspelled that. I wonder what package it just installed when I ran that. Okay, that's a problem for after class. The diamonds data set I jokingly referred to yesterday is one of these, special data frame objects. A tibble is a type of data frame, but basically what you need to know is that a data frame is a rectangular data structure that's designed for typical statistics usage. It's generally assumed that your rows are observations and your columns are your variables. And the nice thing about data frames is that the variables can be different types. And so we see here, we've got caret, which is clearly a numeric. We've got cut, which is some sort of categorical variable. We've got color, which is also categorical. Clarity, also categorical. And then depth, table, and price are all numeric. I don't even know what table means, but I showed that matrix Y earlier. Everything in Y is numeric. A matrix is a simpler data structure that can only handle one type of data. And so everything has to be a numeric, or everything has to be a character, or everything has to be a true false, but you can't have this mix of different types that we can have in a data frame. Okay. And like I said, a lot of the time when you're working with R, the thing you're going to want to do is pull your data in and make it a data frame. That's often step one. And there's a nice interactive, you can't see it when I'm zoomed in this much. Keep going. Where is it? Oh, it's up here. Ah, there it is. This import data set button up in the top right is often going to be the quickest and easiest way to do it. And the nice thing that I didn't mention yesterday about import data set is when you do it, when you actually use it to bring in a data set, it will also give you the code to do that sort of from R natively. So if you want to say create an R script that is fully reproducible and anybody else could, reproduce your analysis line for line, the import data set functionality will give you the necessary code. And so that's the other reason why I'm not really going over the coding ways to pull data into R, because you can do it and you can generate that code without really having to know how to do it. I do this a lot. All right, sit back in. Okay, that said, if you've ever worked with real world data, it can be messy. We're often not in this situation where we've got a perfect rectangular data matrix where all of the observations are independent and we've got full, complete information about every row. Oftentimes you're pulling data from multiple places, right? Maybe you're pulling, you've got your own survey that you did, but you want to overlay that with zip code level information, or you want to overlay that with country level information, or you want to overlay that with something else that you pulled from some other source. And this general process of getting your data set ready for analysis is called data wrangling. And that's basically what this is about. I'm using Eric's slides today, but I would have titled this data wrangling. Day 2 is about data wrangling. But the way that we're going to do it is with a really nice package called dplyr. And dplyr is part of the tidyverse, which, I shaded a little bit yesterday, but dplyr is absolutely like foundational. dplyr is a real workhorse in terms of data wrangling. It can do things that would be very, very difficult to do by hand or to do, manually with your own handwritten code, and it can handle them quite easily and effectively. So that said, unfortunately, we have to start with some more subsetting. This is, the Wikipedia definition of data wrangling, but it's essentially what I said. We want to get the data from whatever format we got it in, which may be, it may be a mess. It might be some PDF. It might be some handwritten thing. We want to get the data from whatever format it's in to something that's easily accessible, easily readable, and easily analyzable. Data frames we already talked about, but essentially they're a very common data structure in R for handling diverse data types. Here's the diamonds data set. All right. So dplyr, like I said, is a package for data wrangling, for getting data in shape to be used, to be analyzed. It can do all sorts of very powerful things, and it can save us a lot of frustration because these are not the types of tasks that you dream of doing when you think of, data science or data analysis. You don't really want to spend time thinking about, well, how do I match these subjects to these descriptors and get them to match up nicely so that I can do this, great analysis that I have in my head. You've got an idea for a project, you know what variables you want, but getting them into a shape that can be used is often very challenging. And that's a challenge that dplyr makes a lot easier. There are a lot of references here. I'm actually going to pull up the cheat sheet because this one I have bookmarked. This is a fantastic resource. If you Google dplyr cheat sheet, you should be able to find it. Fine. Here we go. Just download it, show it in a different window. Yeah, this is fantastic. This is a complete guide to, that's what I was looking for. Not a complete guide, but it's a very good and very thorough visual guide to the types of things that you can do with dplyr. And I think it's helped me a number of times. And if you're ever confused, like this is a good place to start. It just introduces a lot of the concepts for things you can do with your data. I should point out that it's 2 pages. The one that I'm always looking at is joins. So these are like for combining data sets by particular variables. Very, very helpful. So with that, we're just going to talk about some of the basic functions. And this is the part where I have to say, I don't understand why some of these functions exist. It's nice, like I said, to have functions that are verbs: select, filter, mutate, summarize, group by. These are, they make it easier to conceptualize what you're doing when you read your code. And I think that's why they wrote these functions. And some of them are very useful, and some of them are just fancy ways of doing subsetting, which we've already talked about. There we go. So if you haven't already, I encourage you to install dplyr the same way that we installed ggplot before. I'm just going to make sure that I have it. No, I already had it loaded. So if you already have a package loaded and you try to install a new version, it'll throw you that little dialog box. Great. And these are all just like little messages that sometimes pop up when you load a library. You generally don't have to worry about them. But now we've got the dplyr package ready to use. And the first function that we have to introduce is select. And it's just a subset. It's just subsetting the data column-wise. Like I said, this one doesn't make a whole lot of sense to me. But as far as I can tell, select x comma y is always going to be synonymous with x indexed by comma y. That's all it's doing. It's selecting particular columns from your data. And so, you know, in the spirit of not writing unnecessary code, like keep your code as concise as possible, I would generally use the square bracket subsetting. One of the nice things that you can do that is a little bit harder is subsetting by name. So, for example, in the diamonds data set, if we wanted to pull out the carat and price variables, this is how you would do that with select. I'm just going to show that that works. That gave us a two-dimensional data frame with just those two variables that we wanted. It's a little bit trickier to do that with square brackets, but still pretty straightforward. Carat and price are not objects in our environment, right? You can always look at the objects that exist in your environment. I've got diamonds, I've got Y, I've got some stuff left over from yesterday. But carat and price are not objects. So if I tried to subset by those, it would give me an error. Right? If I just ran this is wrong for several reasons, right? Because we've added another comma now, so it thinks it's a three-dimensional thing rather than a two-dimensional thing. This is just all kinds of wrong. But the first error it throws is carat not found. So this is pretty non-standard evaluation. Like, another reason why I don't care for these functions is that this is code that is very, very specific to the tidyverse. This code that looks like this wouldn't work in other contexts because carat and price are not objects in your environment. So if you wanted to subset by the names of the variables using square brackets, you have to use the concatenate function that I introduced yesterday. And then you also have to put quotes around those names. Yeah.
X, would that be diamonds or what is it?
Oh, sorry, it should be diamonds, you're right.
Oh, okay.
X, the only reason that wasn't giving an error was because I had a value called X that was that numeric vector from earlier. But as soon as, yeah, you can see this error pointed out the same thing that you caught. Like, you've got the wrong number of dimensions because I had this comma in here and X was a one-dimensional vector. But if I say diamonds, then we've got the same two-dimensional data frame. Yeah, good catch. Okay, so that's select. It's for subsetting columns. Similarly, filter, which I don't understand why one of these verbs is for columns and one is for rows. Like select and filter seem like very similar meanings, and neither one of them sounds like it's specifically talking about the observations rather than the columns. Somebody online mentioned that they couldn't find the function select, but they had installed the dplyr package. I'm going to remind you that you need to load it with the library function, and that should solve the issue. But just like select, filter is purely a function for subsetting, and rather than columns, it does rows. So filter x comma y is basically exactly the same as x square bracket y comma, right? This time the y is to the left of the comma because we're subsetting the rows rather than the columns. And there, yeah, one of the nice things again is that you can subset by true and false. And so if your y is some sort of comparison, like I'm going to make sure that I use the diamonds data set this time. Diamonds such that diamonds $caret is greater than 0.3. We've now only got whatever 49, well, plus the 10 that were printed, we've got 49,747 observations, whereas before we had 53,940. So it's hard to see because it only prints the first 10 rows because it doesn't want to overwhelm your screen with printing stuff. But we've subset down to just those observations where the caret value is greater than 0.3. And that's, yeah, you can do that slightly more concisely with filter, because you don't need to specify that I'm taking the caret variable from the diamonds data set. You can just say caret and treat it as if it's already an object in your environment. I just want to point out that that's non-standard. That's specific to dplyr or tidyverse. Okay. Just another example. This time, we're creating multiple conditions, and this is again something that you could do with both the filter function and with subsetting, but you can make more than one comparison. And so a couple of very important things are happening here. First, this AND operator. So the AND operator is a way of combining true-false values, right? If we've got two numeric values, you can combine them with the plus operator, or you could combine them with the multiplication operator or the division operator, right? Those are ways that we can combine or compare numeric values. For true-false values, there are two important operators, and that's and or. And so the ampersand is and then there's a vertical bar, which on a Mac is, if you hit Shift backspace, it should be just above the return key. There's that vertical bar, and that means or. So for example, if I've got true and false, and I evaluate this, it's going to tell me false because we need both of them to be true in order for the and to be true. If I say true or false, it'll evaluate to true because at least one of them is true. And much like before, we can do these with vectors. And so what's actually going on here is we've got two vectors. This one, clarity equals IF for internally flawless, apparently, and cut equals ideal. Both of these are going to return numeric or return true false vectors. So if I just take one of them and then add this so that it's actually recognized as an object in my data set, it returns a very, very, very long vector of trues and falses. And so one other thing that I need to point out here is this double equals sign. There's a very important distinction between a single equal sign and a double equals sign. And that is that if you want the output to be trues and falses, if what you're trying to do is check, does this variable equal this value, then you need to use the double equals sign. The single equals sign is used generally inside of functions. So if I go back to LM, remember LM is our linear models function. Inside the call to a function, that's generally the only place you'll ever use a single equals. And it's for saying, it's for specifying arguments to that function. It's for specifying additional information to that function. So if I wanted to set, you know, any of these arguments that go into the LM, I don't have to use all of them, right? I don't have to specify anything more than just like X and Y. If I give X and Y, then LM will generally know what to do. But there are all sorts of little tweaks that you can make to how that function works, and you specify those through these arguments. And if you want to set the method, you would say method equals, and then some value that is a valid quantity. So single equal sign, it's for specifying how a function should work. Double equals sign is for checking. It's for asking the question, does this equal that? So getting back to our example here, this is doing something pretty profound, right? I'm going to go ahead and add a second set of parentheses just to make it clear. We're filtering the diamonds data set, which again just means subsetting the rows. And we're subsetting the rows based on clarity equals IF and cut equals ideal. Both of these things have to be true in order for that observation to then be included in the output of this function. So if we do that, we assigned it with this assignment operator to a new object called diamonds underscore fine. And we see that that's a data frame, much like the data frame that we had before, but this one's much smaller. It's only got 1,212 rows. Whereas before we were over 50,000. So it's a much smaller data set because we subset down based on these two different criteria, both having to be true. Okay. Mutate is where we start to get into some of the fun stuff. Mutate lets you create a new variable. And it would be pretty easy to do this in base R, I'm not gonna lie. But because you can treat the names of columns as if they are objects already, then sometimes mutate can lead to shorter code, which can be nice. But essentially, this is a way to either change an existing variable or create a new variable. I'm just going to show an example here. So if we've got, ignore the underscore 4C for now because we didn't create that. But if we've got the diamonds data set, which we do, and for some reason, let's say we're fitting a more sophisticated model, right? Let's say we're fitting a model that uses a squared term and a cubed term for caret. And so it's some sort of nonlinear model in terms of, it's linear in terms of caret squared and caret cubed. But for whatever reason, we want those two new variables that are based on old variables. This is how you would create them. Or rather, this is one way in which you could create them. So zoom is in the way. There we go. So this is how you would do it. It's essentially mutate, which is the function that allows you to create new variables, the name of the new variable that you want, and then some expression that tells R, how do I create that new variable based on old variables? And so if I do that, it outputs a new data frame, which has 12 columns now instead of the 10 that we had before. And the new ones get cut off because of the way it prints, but you can see it says down here, 5 more variables, and it starts listing them X, Y, Z, caret squared, and caret cubed. So we've created these 2 new variables, caret squared and caret cubed, that we didn't have before. And so that's why there are 2 extra columns on our data frame. Importantly, we didn't save it, right? I said to mutate that data frame and do it this way, and it did, and it output a data frame, but it didn't have anywhere to store it. So it just printed it to the screen. It's not anywhere in my R environment. If I pull up the diamonds data set again, which is the one that we just mutated, we can see it only has 10 columns. And that's because we didn't store the output of that previous command anywhere. So when you do that, it'll print it to the screen, but it won't save it in an object. So if we want to save this, we need to do like we did before and use the assignment operator. So new diamonds gets this. If I run this line of code, notice it doesn't print anything. It only printed the code. It didn't print the output of the code. And that's because the output was being assigned to this new variable called new diamonds. Similarly, you can change existing variables. I think this is pretty straightforward. But we saw before when we used caret squared and caret cubed, these were names that didn't already exist in our data frame, right? These were new names that we didn't have before. If you give it a name that already exists in your data frame, you're going to overwrite that variable. And so here, all they're doing is taking the clarity variable and converting it to a numeric. So that's what as.numeric does. I think because it was an integer before. Let me double check that. Clarity. Oh, it was an ordinal. So it was an ordered categorical, which is like if you've got, categories of things that go from low to high, you might make that an ordinal variable. But here they're converting it to a numeric. So the lowest category will get a 1, and then the next category will get a 2, 3, 4, 5, all the way up to however many categories there are. You could also do, mathematical operations like we did before with squared and cubed. You could do, any valid R code on this side. A good example for when you might want to use this would be, say, converting currencies. So if we were trying to convert all of the prices in this diamonds data set to yen, and we had the conversion rate at 106.6 to 1, then we can create a new price that is 106.6 times the old price, which was in US dollars. And that'll create this, which is a price column represented in yen. Any questions? Oh, and just quickly, the regular like base R way to do these things would be just to specify diamonds dollar caret squared equals diamonds dollar caret squared. So like before, if I specify a variable that isn't in my data frame, oh, I should say gets rather than equals. If I specify a variable that isn't in my data frame and I assign a value to it, then R will know that should be added to the data frame. And so this would be the way to add that caret squared variable to the data set without using mutate. It's, yeah, again, very similar, except for the fact that we can't treat variables in the data set as if they are already R objects in our environment. We have to specify, I'm talking about the caret variable from the diamonds data set. Okay, any questions before we move on to summarizing? Seeing anything in the chat? So summarize is where things start to get good. This I can wholeheartedly endorse. This is a way for, as you probably guessed, summarizing different elements of your data. There are lots of different ways that you might think about summarizing a data set such as this, right? What's the average of each of the numerical values? What's the relative proportion of all the different categorical values? How many different types of each thing do we have? A lot of ways that you might be interested in sort of breaking down and looking at different aspects of this data. So what summarize does is it takes your input data set as sort of the raw data set, and it creates a new table of summary statistics. It creates a new data set. We're not interested in modifying the old one now so much as creating some new way of thinking about that data. And so it's going to create a summary statistics object. Much like before, the first argument is the data set that we're working with, right? X in this case is going to be our data frame object. And so that's pretty much universal across the tidyverse. The first argument is the data frame that you're working with, and then everything after that is what you want to do with it. So here f is any function and z is a particular variable in the data frame x. And so there are a lot of different R functions out there, but some of the ones that might be useful when we're thinking about summarizing data are the sum, mean, median, min, and max, right? A lot of different things you could do. These are just maybe some nice ones to start with. They also allow for the British spelling. Yeah, this is a simple example where we just want to look at the average price across all of the diamonds, all of the observations in the diamonds data set. We're going to say average price, that's our new variable, equals the mean of the price variable from that diamonds data set. And what it outputs is a new table. It is a new data frame, but it's just one by one, because all it contains is that one value, which is the mean price, the average price. It's a fancy package for a single number, but we're going to see why this is helpful later on when you want to summarize multiple things, or you want to summarize different, by different groups. You can also provide user-defined functions. So mean is a built-in function. That's something from R. We didn't write that function. But if you want, you can write your own function. And we're not going to get into like how to write your own functions, because this is, I would say, more advanced like software development. But if you have a function that you've written yourself, or that you've taken from the internet, or wherever you might have gotten it, maybe it's from another package that you've installed, you can also use those functions in here to do whatever summaries you want. And so this is doing the sum of squares, SSQ. It's taking the sum of x squared. And if we apply that inside a call to the summarize function, we get this gigantic number, which is the sum of all the squared prices, right? Which are already pretty high to begin with. So gigantic number. As I previewed before, we can also do multiple summaries. So here we're doing mean and median price. One thing to note is that it does drop other variables, right? We had a bunch of different variables. We had cut and we had clarity and we had other things in this diamonds data set, but the only things that get output by summarize are the things that you specifically asked for: mean price, median price. Yeah. This is an important point, actually, that it takes a vector, that's the input. Whoops. Right, price here is one column from our data set, so it's a vector of values. And it outputs a scalar, which is a single element. You could also think of it as a vector of length 1. Okay. The point at which this sort of gains a new level of utility is when you combine it with group by. And group by is another one that I can wholeheartedly endorse. But it's essentially when you want to group your data by a particular element of that data. So if you wanted to do some sort of subset level analysis, right? I want to do this operation for these observations and these other observations, but I want to treat them separately. Group by is the way you would do that. So first, let's just see what it does. So remember that cut is one of the categorical variables in our data set. We're going to run this line of code, which is just grouping the diamonds data set by cut. And then importantly, it's assigning that output to a new object called diamonds underscore cut. Oh, got a message. Can you summarize critical values, for example, prices for cuts? I think this would be oh, sorry, for those in the room who probably can't read this small text. It says, can you summarize critical values? For example, prices for cuts between 2.3 and 0.5. I'm not entirely sure what you mean by critical values, but I think yes, this would be a matter of subsetting down to those that have cuts within that range. And we've seen how to subset based on a logical comparison before, and then summarizing that subset of the data. Okay, so getting back to this line of code, we wanted to group our data set by cut. And what that gave us is a data set of the same dimensions as what we had before, right? We didn't lose any information, but now it should be grouped by cut. Oh, did this not do what I thought it would? Oh, okay, it's hidden, it's metadata. So the groups are up here. So there's some sort of hidden information here, which is what this data set is currently grouped by. If we look at the original diamonds data set, we didn't have that. And so here it's just letting you know this data is grouped by cut. So if you do anything to this data now, by group, it will output 5 values, 1 for each level of that variable. And so now if we do the exact same line of code from before, well, almost exactly the same, we want to summarize and we want to say, give me the mean price and the median price, but rather than the original diamonds data set, we use the diamonds_cut data set, which again is exactly the same except for this group's metadata. What we get out is now a rectangular data structure. It's now a 2-dimensional data object where we've got a mean price and a median price at every level of that cuts categorical variable. We did that again, just to reiterate, on the original diamonds data set, which wasn't grouped, we would only get the overall mean and overall median. We can stack things, we can do more than one transformation. I think this might actually be a better answer to the question that was asked online a minute ago about summarizing a subset of the data, but we can chain things together. That's what diamonds 4C is. So if we want to create a data frame that only has the 4Cs, cut, color, clarity, caret, I wonder, yeah, I am not a jeweler, so when I saw that 4C earlier, I had no idea what was going on. I apologize to any diamond aficionados in the crowd. Okay, but what if we want to filter based on cut and clarity? We kind of showed how to do this before. It's just with the filter and then this and operator. And here we're not using the extra parentheses because we're not trying to be super clear about what's going on, but it's the exact same comparison that we had before. We're relying on the order of operations here. The double equals sign is going to get evaluated before the and gets evaluated. So there's probably some mnemonic extension of PEMDAS that tells you how these different things get evaluated in certain orders, but generally I just go a little overboard with the parentheses to make sure that things happen in the order I want them to happen. Here's a different way of doing that same thing. So remember, we did select to get these 4 C variables, and then we did filter to get just those that have an ideal cut and internally flawless clarity. We could do that in one line of code by nesting these calls. So first, the thing on the inside gets evaluated. The first thing that happens is we're selecting the cut, color, clarity, and caret variables. And then that's getting filtered based on cut and clarity. We also saw this yesterday, actually, when I showed hist of R norm 1000. Remember, R norm is random normal. So this R norm 1000 is just going to create 1000 random numbers drawn from a random normal distribution. And then hist is the histogram function. And so this is going to create a histogram if I make this big enough to actually show a histogram. There we go. It's going to make a histogram of those 1000 random values. So we've seen this a couple times now, but just know that there's a lot of power to be unlocked in nesting function calls like this. And it can make your code a lot easier. Because the alternative here, the alternative to this nested function call is to do exactly what they did in naive solution 1, which is create a new object and then use that object in the next function call. And if you do that, it would look like X gets, people are joining with 7 minutes left. R norm 1000, and then hist of X. And this is going to do exactly the same thing, but we've sort of cluttered our environment with this unnecessary X variable that, you know, we didn't really need. We only wanted the output, which was the histogram. So if you do this too much, you can end up confusing yourself. And I do this to myself all the time, like literally all the time. So just know that that's sort of the benefit of these nested function calls, or as I think we're about to see, piping. And these slides are now out of date because the pipe operator was something that was introduced by tidyverse, and it's for chaining function calls together. It's for piping the output of this function into the input of this other function. And it was so popular, and it was used so widely that the people who manage the R language itself decided we should make our own pipe. We should make this like an actual foundational part of the language. And so now there's this, which is the R pipe operator. But basically, anytime you see percent, like a percent arrow like this, that's the same as this bar arrow. Both of them are pipes. The only difference is that this pipe with the percents comes from a package. And so you have to have that package, which is called magreader, loaded in your R environment if you're going to use the percent sign pipe. This is another reason why all of the tidyverse functions use the data object as the first argument. The first thing that goes into any function in the tidyverse is the data frame that you're working with in that moment. And that's because the pipe feeds into that first argument. So if you've got a function, you know, here we've got a data set X, and we're piping it into a function F, and the output of that is being piped into a function G. If G takes 4 arguments, we're only specifying the first one. The pipe goes to the first spot in that function call. So basically, to make that a little bit more concrete, if we take a data set X and pipe it into the select function, and we just say y, right? We just say the index by which we want to subset our data, it's going to know that actually x is the first argument here. So x pipe select y is the same as select x comma y. Whatever gets piped in sort of bumps these arguments one space later. So this would be another way that we could solve the problem of before, where we wanted to trim our data set down to these 4 variables and then filter the observations based on clarity and cut. We can take the diamonds data set and pipe it into the select function, and then we skip the part that we had before, right? Before, when we did select, go back to find it, diamonds was the first argument, but we don't need that anymore because it's being piped in. So diamonds is implicitly the first argument here, and we're selecting the variables cut, color, clarity, caret, and then we're piping the output of that into filter, and we're filtering based on these 2 criteria. Here's sort of another thing that we, oh yeah, sure.
How we should do, how should we do if we want to cheat Carol as a vector of the left of the pipe function? I mean, in this case, you cheat diamond, you put diamond on the left of the pipe function, but what about what should we do if we want to put caret or one of the columns of diamond on the left of the pipe function?
I'm not sure I understand the question. The pipe function has a directionality. It's their arrow, like both of the pipe operators look like arrows pointing to the right, and that's because they have a very specific directionality. We're taking diamonds as the thing that gets piped into the select function, not the other way around.
No, I mean, color, clarity, all of these ones are the columns of your diamond, right? Yeah. How should we do if we want to put these columns on the left of the pipe?
Why would you want to do that? What would you be trying to accomplish? I'm sorry, I don't think I'm understanding correctly. Anyway, like I said, all of these, since most of you have installed R recently, you should have access to the native R pipe. It looks like that. This should work, and it does. And so now we've got this diamonds solution 3, which does the same things that we saw before. Takes the diamonds data set, selects particular variables, and then filters. Okay, that's all that I have time for today. Tomorrow we'll do a little bit more, maybe do a little bit more plotting, because we sort of shortchanged that the other day. But we're going to talk about reproducible documents and sort of how to make nice documents that interweave code and text. So how to generate pretty reports basically with R. All right, thanks for joining. Stop the Zoom meeting.